Today I'm reading Examining the Benefits of Capsule Neural Networks. From the authors are Punjabi, Schmidt, Agelos, Akatsagelos. It's from Northwestern University, Electric Engineering for Communication Systems, HSR, University of Applied Sciences in Rapperswil. Abstract. Capsule networks are recently developed class of neural networks potentially addresses some of the deficiencies with traditional convolutional neural networks by replacing the standard scalar activation with vectors and by connecting the artificial neurons in a new way. Capsule network aims to be the next generation development for computer vision applications. However, in order to determine whether these networks truly operate differently than the traditional networks, one must look at the differences in the capsule features. To this end, we perform several analyses with the purpose of elucidating capsule features and determining whether they perform as described in the initial publication. First, we perform deep visualization analysis to visually compare capsule features and convolutional neural network features. Then we look at the ability for capsule features to encode information across the vector components and address what changes in the capsule architectures provides the most benefits. Finally, we look at how the capsule features are able to encode information parameters of a class objects via visual transformations. Introduction. Convolutional neural networks (CNNs) have long been tools of choice when tackling computer vision problems. The spatial localization of CNN features is greatly beneficial when the networks are applied to images and videos. However, these networks also have their shortcomings. The kernels in convolutional layer must learn to identify the presence of all relevant features in the input. Thus, transformations such as location occlusion can be determined when the training dataset is not properly augmented. Even still, the burden of running visual features in addition to all possible modifications of these features can be immense for a traditional CNN. Recently, a novel class of neural networks we proposed in one that employs the concept of the capsule. The authors describe the capsule as a group of neurons that represent the existence of feature in addition to parameters regarding the instantiation of said features. Contrary to scalar activation of kernels in traditional CNNs, the capsule networks aim to be representations of informations in the network. In this manner, Capsule should be able to encode not only the existence of a particular visual feature, but also the transformation that it undergoes in given application. So my basic summary of the capsule networks is that they give a stronger prior than CNNs on the input, where they expect some sort of that you have some sort of 3D objects. You have this prior that you are looking for some 3D objects, and the rotations and translations and so on are then estimated by the network. For example, CNNs, they are invariant for translations, up and down, right? But they don't have this rotational, they don't inherently have inside of them this rotational symmetry. So when you rotate an image, there is no sort of transformation in CNN where you sort of rotate your kernel, right? And as well, you don't have some sort of 3D transformations in the CNNs. You don't have this symmetric group there supported in the network. You don't have the prior there. So, if you restrict the function space for the neural network, it should be easier. You should need less data to train this network. Okay, end of my summary, and I continue reading. That said, while initial results showed great potential for capsule networks, it is still uncertainty regarding how these capsules function. In fact, the black box analogy can be applied to all classical classes of neural networks, not just those with the capsules. The interpretability of neural networks has always been a problem. It is difficult to examine the benefit of the capsules without the comparison to traditional CNN features. In an attempt to elucidate this feature, this investigation will begin employing a deep visualization technique to generate images that visually represent the information contained in the capsule. This image can be then compared to an image created with a similar fashion from traditional CNN, and the discrepancy between them can provide the visual justification for hypothesized benefits of the capsule networks. Furthermore, the visual impact of the modifying values in the capsules are examined to be more accurately ascertain their capacity. Finally, the investigation will examine other facets of the original capsule network architecture proposed in one, namely the benefits of the dynamic routing and reconstruction network. Next section highlights the related work in the field, followed by the outline of capsule network and visualization methodologies. Finally, the results are shown and resultant trends are discussed. So I will skim through the related work. The concept of capsule network originated in Hinton's paper 2017, when the capsule networks are described as implemented with the convolutional architecture. Furthermore, dynamic routing algorithm is proposed that selectively links units in the capsule together rather than traditional downsampling methods such as max pooling. There is a follow-up publication, Hinton 2018, that extends capsule to matrix form as well as further developing the routing scheme. However, our work will primarily focus on the architecture discussed in the first paper, and our experiments will be in parallel to those performed in the first publication. Other modifications to the original architecture have also been proposed, including 3, where the capacity of the network is increased via both layer size of capsules, along with the changes to the activation function. The authors in 4 demonstrate that the capsules with masking operation in 1 may be generalized better. The work in 5 extends the capsule scheme to a multi-scale hierarchy. A generative adversarial network is proposed in 6 that makes use of capsules as a discriminator network. The network in 7 takes hyperspectral images as an input as opposed to standard RGB. The authors in 8 create a CME capsule network by combining pairwise inputs with the capsule architecture. The application for capsule networks had been widespread. In 9, capsule networks uses images taken by UAV for classification of rice fields. Detection problems were found to find street signs in 10, while authors in the 11 use capsules to analyze traffic patterns and density. The work in 12 outlines capsule network for seagrass segmentation and satellite images. Video data is used, and so on, so on, so on. Despite their relative nascency, many have started using capsules in medical domain, including segmentation, cancer detection, CT, learning diagnosis problem. Clearly, capsule networks exhibit great potential, yet the justification for how these networks perform is less clear. Hunton enumerates several potential benefits of capsules, namely that increased dimensionality of capsule allows feature transformation and encoding, and the dynamic routing is more intelligent way of aggregating information. That said, the experimental results, while impressive, are not necessarily proof of that capsules are exhibiting these traits. One set of experiments in one seems to indicate that the certain object features can be controlled via capsule manipulation, but this is not exposed to greater depth. The authors in 23 make more concerned attempt at the explainability by varying output capsules in more than one dimension, but yet again this methodology is somewhat limited in the scope. Our investigations compound on these capsule manipulation experiments by adding deep visualization techniques. Primary techniques: activation maximization. We will not extend much beyond activation maximization structure. Fundamentally, the applications of activation maximization to capsule network for purposes of understanding benefits of traditional CNN is a nascent investigation. It's paramount methodology. To begin, our investigation applies the deep visualization technique of activation maximization to the 2 trained neural networks, capsule network and CNN, with comparable computational power and information capacity. By comparing the resulting images, we are able to distinguish the different features of representation in the 2 networks and glean insights into the potential benefits of the capsules. The second experiment further scrutinized the capsule features in order to directly ascertain whether the capsule vectors truly model the transformation parameters. Okay. Capsule network architecture. I think most people know this one, right? So we have these capsules within capsules. and then you have these routing algorithms which take the capsules from the upper layer to capsules in the folded layer. Alright. Coupling, routing softmax. The coupling coefficients C used in the dynamic routing process are given by routing softmax, where B, I, J are logits of the coupling coefficients that are iteratively defined by routing algorithms proposed in 1. The initial logits are set to 0 in all experiments. In doing so, the coefficient converges towards the agreement of the output of one of capsule with output of a capsule in the previous layer. After the class capsules are found, the L2 norm is used to find class probabilities, which in turn are used to make final classification. While this is entirely the network of testing time, it is trained with the reconciliation network that takes the output of the largest capsule vector corresponding to the classification label and applies 3 fully connected layers. Yeah, let me go back to this routing by agreement. I actually don't remember it that well. The class capsule layer follows primary capsule layers, and at this point where the dynamic routing algorithm is implemented. This routing by agreement serves as a more advanced method of neuron connection as compared to traditional methods like max pooling, which can lose all but the most prominent connections. Okay, activation maximization. After the network is trained, activation maximization can be used as a means of visualizing features learned by the network. In general, activation maximization is optimization approach to produce images that can represent either intermediate network features or object classes. It can be formulated as energy compaction. Okay, actually, let me describe the image. So on the top left, we have MNIST numbers. Specifically, here we have a square of different versions of 4 character, and those are then passed to the capsule network. Then from a capsule network, it goes to a PCA. We get the variance estimate, and then we display explained variance and principal component numbers. And as principal component numbers increase, the explained variance goes down approximately exponentially. Okay, I will skip this. Energy compaction. While activation maximization images provide method to visually examine a network feature, the energy compaction analysis outlined here presents a more quantitative comparison. After capsule network is trained, a set of images is passed through in order to obtain corresponding capsule vectors. Principal component analysis PCAs perform on these vectors, following which the variance along each of these particular dimensions is found. One can see the diagram of this pipeline in figure 2. I just described the image. This variance is a measurement related to the distribution of energy or information along specific principal axis. If the information is heavily concentrated in one particular direction in the native capsule space, the variance along the first principal component will be disproportionately large. This in turn indicates that the number of dimensions required to represent the information is small, with perhaps even just one dimension being sufficient. In this investigation, the phenomenon correlates with the capsule vectors that do not encode the information across all dimensions in the capsule space. Rather, these vectors only encode information in a small number of dimensions. Because the capsule vectors proposed in 1 are supposed to store instantiation parameters, this may indicate that the capsules are not functioning optimally, thus the benefit of over traditional CNN feature may also be limited. The converse is also true. When information in the capsule vector is well distributed, the variance along the principal axis will be more balanced. Granted, any PCA will yield components that have decreasing variance as the component number increases. However, the slope of the trajectory is more gradual in this case. Consequently, many, if not the most, components are required to present the information in the capsule in the vectors. This potentially correlates with the capsule vectors that are functioning optimally and suggests the benefit over CNN features in line with findings in paper 1. Transformation, encoding, forward analysis. The forward analysis begins with a manually generated set of transform images. One can see that the example of figure 3 where the MNIST dataset is manually transformed with varying degrees of rotation. Pre-image analysis. The term pre-image has been used in several ways in deep visualization literature. Here we use term to define images whose capsules vector is more closely matched to particular target. Continuing the example described in figure 3, we see in figure 4 that the pre-image analysis aims to find images that match some target values when passed through the network whose capsule vectors are then transformed into PCA space. Okay, so again we have the image 3, we have rotated numbers of 5, then it goes to capsule network displayed by PCA. They look at second principal component and they display it in the scatter plot with the first principal component. And then in the scatter plot they show two different lines, which I guess represent different rotations. And then they get this to one starting point of 0 degrees rotations and two final points of 45 and minus 45 degrees rotations. And so what does this say? I'm not sure. Let me find figure 4 description again. In figure 4 we see that the pre-image analysis aims to find images that match some target values when passing through the network whose capsule vectors are then transformed into PCA space. While the objective of forward analysis was to generate transformation curves in PCA space, the objective of pre-image analysis is to ascertain the ability of control visual transformation via capsule vector modification. The ability is to do the claim. In figure 4, the green points represent modified capsule vectors in PCA space. In this particular case, the original digit without rotation, the purple, had the second principal component values modified with varying degrees to form a set of pre-images. As modified activation maximizing procedure perhaps more accurately describe the activation matching procedure to find corresponding pre-images. Well, I would sort of expect that one of these components would actually correspond to the degrees of rotation. So I would sort of expect that we would have this purple, and then there would be one sort of component where we would go in one direction when we increase the rotation, and then to another direction when we decrease the rotation. It doesn't seem to be the case in the picture here, but maybe I'm misunderstanding. The results and discussion. The capsule network was trained on MNIST dataset on have written digits in the same manner as one. Therefore, the 10 capsules in the final layer each correspond to a particular digit. The when capsule vectors need to be executed for the PCA procedure, suspected growth of capsule matrix taken for the processing the network itself, but the activation, maximization, and pre-image algorithms to form a regularization were used. First, a median filter of kernel 3 to 3. This regularization ensured images were interpretable and stayed within the distribution dataset. Okay, comparison of classification methods. Okay, I'm gonna skip forward. Activation maximization here. Section B. As discussed, the activation and maximization analysis aims to create images that represent the information learned by the network. Figure 6 shows the 100 such images created from activation, maximization, and algorithm when applied to capsule network, both with and without the reconstruction network, as well as 100 from baseline CNN. These images are stacked and stored in 10-tag grid, this decreasing value activation score. Thus, the top left image has activation value. 100 trials recall the activation maximization implements the aggregation of features that the network has learned to represent the particular class. See, the visualizations are indicative of class in question of the image, so defining characteristic of 6 digits in both circular loop as bottom tail. This shows the capsule network. Okay, let's look at the images. Yeah, so I see the 6 capsule network, strong reconstruction. This is very, very clear 6 reconstructed. Very, very nice 6. Then we have a capsule network, no reconstruction. Well, that's you could sort of say that there is a 6. If you know that you are looking at numbers, you would say that you're probably showing 6, maybe 0. And CNN activation maximization would be very difficult to say what you're looking at. Maybe you could guess that it's 6, but it's almost impossible. This contrasts to activation maximization images from CNN, as shown in figure 6. In this case, features that the network uses are much less clear. Generally, it can be seen that CNN has some general oblong shapes in the lower half of the images likely to relate to the circular loop. That said, the clarity of these loops are far worse. This supports the notion that CNN is only searching for oblong loops in the bottom of an image to classify 6. Given CNN's proclivity to find lowest complexity feature required to determine the between class, this phenomenon is fairly logical. That said, it's consequently important to look at this distinction in context of differences between capsuling and CNN. Both networks compare tasks very well, each obtain over 99% classification accuracy. Thus, the difference in visualization can be attributed to feature complexity rather than classification power. Therefore, there are indications that the capsule feature space capture more information from a class of its CNN counterparts. Fundamentally, the capsule features demonstrate an understanding of the class exemplars to much greater extent than the CNN feature, which is aligned with the ideas in the paper 1. Okay, I would like to find out what they mean here by the strong reconstruction. Furthermore, in addition of a strong reconstruction, so first, in more cases, furthermore, addition of strong reconstruction and routing does improve the performance. It is important to note the relative importance of these components. No routing is applied. When the network does not use the reconstruction component, the corresponding term in the loss function is set to 0. Strong case 50 times larger than weak case. Does not use the reconstruction component. Okay, what is reconstruction component? I'm just gonna make this quick search. Okay, so by reconstruction network takes output of the largest capsule vector and applies it to three fully connected layers. I guess by strong reconstruction they mean that they have this strong fully connected network after it. So when they do this, if I understand correctly, when they do this they get these really nice sixes. When they have no reconstruction applied after the capsule network, they get these ugly sixes. But they still do better with ugly sixes than the CNN. Okay, I'm gonna skip these: energy compaction, transformation encoding, principal component numbers, routing, strong, weak. Then they look at these principal components. Conclusion and future work. As shown, capsule network features do fundamentally operate differently than CNN features. In activation maximization analysis, one could see the capsule features were better able to describe all facets of a class object than the CNN feature. That said, reconstruction was removed from the capsule pipeline. The features degraded and did not have such a discriminative power. In the energy compaction experiment, we showed that the capsule routing and reconstruction were adept at spreading information across all elements of the capsule network. As the reconstruction weighting was reduced, so did the information become condensed within one or of two principal components, which is more in line how a scalar CNN feature may behave. Finally, the transformation encoding analysis showed that the capsules are indeed able to capture instantiation parameters of class objects, which is a major benefit of over CNN features. The sum of these experiments showed that the capsule features do have the potential power to surpass CNN features, but it is important to know that the reconstruction part of the network is still essential for desired behavior, whereas the dynamic routing algorithm may not be as beneficial. The further the work started in this investigation, applying these techniques to the more complicated data may produce the more discernible features classification rates. It may be offers great ability to compare features and better performing network would naturally have more discriminative power, but there may be benefit having an experiment performance of the networks do not exceed 99% classification accuracy. Additionally, given how the important construction network was through capsule performance, it may be valuable to combine these results with an CNN that similar induced reconstruction network for regularizations. Finally, looking at the more advanced capsule architectures, such as those with deeper capsule connections or with a different routing scheme may be valuable. In this manner, we could truly ascertain whether these networks are in fact the next stage of evolution in the computer vision tasks with neural networks. Alright, so this will be it. I'm just gonna have a glance if I could. So they sort of claim that they can the principal component somehow, I guess they mean that they somehow correlate with these rotation things. Or maybe here in this C rotation, you can see that the purple in the second component is sort of below the blue point and above the green point, indicating that maybe the second component is the correlates sort of with the rotation. Scale modification in the picture here. They are showing, I guess this could be, I don't know, no, not quite sure. Maybe there is some sort of relation. I don't see it. Maybe you could read more deeply. Thank you for listening. Let me know if you have any suggestions below in case you are still listening. And yeah, maybe see you next time. And yeah, thank you very much. Goodbye.